So good day guys, I'm going to discuss about the Euler circuit. So what is Euler circuit? It's used to determine whether it's possible to pass over every edge in a graph exactly once, but while beginning and ending at the same vertex. Euler's sum of degrees theorem is used to determine if a graph has an Euler circuit, an Euler path, or neither. An Euler circuit is a circuit that uses every edge of a graph exactly once. An Euler path starts and ends at the different vertices, and the last one is an Euler circuit starts and ends at the same vertex. So now we wanna find a Euler circuit on their graph before. So an Euler circuit is very similar to an Euler path, except that we must return to the same vertex because it is a circuit. So again, the idea is we're going to visit every edge once with no repeats. So, okay, let's say we will start here. 1, maybe 2, 3, 4, 5. So guys, remember, it's okay to visit the same vertex but not the same edge, alright? So 1, 2, 3, 4, 5, 6, 7, 8, and the last one is 9. So we did it. So we have visited every edge exactly once. And now this type of a drawing is sometimes called unicursal drawing, because you can draw the entire thing without lifting your pen, right? If I had started over here, yes, I could draw this entire circuit without lifting my pen once, and that's one of the features of an Euler circuit. So we have another example. Sorry guys. So let's say I'm going to start here. 1, 2, 3, last one 4. Okay, it's that simple, right? Okay, so I'm going to erase this and then clear. Alright, so the next one is the Euler's formula. Says that e to the jx equals cosine x plus j sine multiplied by x. So look at this equation a little bit more. So this is the expression that relates exponentials that will have the cosine and the sine rather. And part of the price of doing that is we introduce the complex numbers into our real world. So where is the complex number? Oh wait, so this is the complex number guys, the J, and this one also. So these numbers are coming to electrical engineering, so we have to mention the other form of this formula, which is e to the I put sign here, e to the minus jx, and that equals cosine x minus j sine x. So these two expressions together are Euler's formula, or yes, Euler's formulas. And we're gonna exploit this by we'll be able to take these cosines and sines, and that we find in nature. We're going to be able to fashion them into exponentials rather, and these exponentials then go into our differential equations and give us solutions. And we're going to come back and pull these cosines and sines. That's the rhythm of how we're going to use this equation to help us to solve circuits. One of the small point I want to share, notice that in both these equations, cosines come first, and the sine is over here on the imaginary side. So cosine is the real side, just here, the real side. This is the reason that we have a preference in the future. We're going to have a preference. If we were talking about the real world signals in terms of the cosine function, it's because it is in the Euler's formula. The cosine comes first in both cases. So what I want to do now is to take a second, and I want to see if we had our signals expressed in these exponential equations. How do we recover the cosine and the sine term? How do we flip these equations around, and so we can solve for the cosine and the sine? It's simple, but of algebra here, it's good to see. Alright, so if I want to isolate the cosine term, right here, isolate the sine here, let me get rid of this guys here. So now I isolate the cosine term. What I'm going to do is to add two equations together, and minus are going to cancel out this term. Right? That's what I'm going for. So if I add the e to the jx plus e to the minus jx, cosine doubles to cosine x, and the two sine terms cancel out. Alright, two sine terms cancel out. Two sine terms cancel out. So then I could write it over here. I can write cosine of x equals e to the plus jx plus e to the minus jx over 2, right? So that's the expression for cosine in terms of complex exponentials. Okay, let's go back and see if we can get the sine. So what I'm gonna do with the sine, and that gives me, what that will do is that get the cosine terms to fall away, and then I get x to jx, e to jx, subtracting, right, minus e to the minus jx equals cosine terms, yes, they subtract out, and I get 2j times sine x, alright, and that means I can write sine x equals e to the plus jx minus e to the minus jx over 2j. and it's really easy. That J term is down there. So that's easy to forget sometimes. So I put a square around these guys. Here. There you go. That's easy to forget sometimes. So I put square around these guys because that's important. So there's the two expression for if you have complex exponential and you want to extract the cosine, then this is how you do it here. And if you want to extract the sine, this is how you do it. Okay? And you can put this in your head, or probably easier for me if you just remember, right? Euler's formula. This is a pretty straightforward, quick derivation. Right? So the other thing, we put a square around this guy. So we have Euler's formula, and basically the cosine and sine extracted from Euler's formula. So that's all. Thank you guys for listening, and thank you.